Appendix to the Autobiography of an Electron by Charles R. Gibson. This LibriVox recording is in the public domain. Appendix. The Scribe's Note on Appendix. As explained by the author in Chapter 1, this appendix has been added for the sake of those readers who may wish further details than have been given in the Electron's story. It is only necessary to give a brief notice of the more important particulars, as the author has written recently upon this subject in a popular form. End of Scribe's Note. It was known 2,000 years ago that when a piece of amber was rubbed with a woolen cloth, the amber would attract light objects towards it. Amber was considered to be unique in this respect. About the year 1600, one of Queen Elizabeth's physicians, Dr. William Gilbert, inquired into this attractive property of amber. He found that many other substances possessed the same property. Indeed, it is common to all substances in some degree. We say the amber or other object is electrified. It was observed by the early experimenters that there were two kinds of electrification. To one of these they gave the name positive electricity, and to the other negative electricity. Every electrified object will attract an object which is not electrified, and two objects which are oppositely electrified will attract one another also. But two objects which are similarly electrified will repel each other. Man got tired of rubbing objects by hand, so he fitted up simple machines in which glass cylinders or plates were rubbed against leather cushions. The electricity was then collected by little metal points supported on an insulated metal sphere. The experiment of attempting to store electricity in a glass vessel filled with water was made at the University of Leiden, Netherlands. The water was replaced later by a coating of tin foil on the inner surface, while a similar metallic coating on the outside took the place of the experimenter's hand. These jars are called Leyden jars, after the place in which the discovery was made. About 1790, Professor Galvani, of Italy, observed that the legs of a freshly killed frog twitched at each discharge of an electrical machine. Later he found that the same twitching occurred when he connected certain parts with a piece of copper and zinc. He believed this to be due to animal electricity secreted within the frog. Professor Volta, also of Italy, proved that Galvani's idea was wrong, and that the electricity resided in the metals rather than in the frog. He showed that when two pieces of dissimilar metal were put in contact with one another, there was a slight transference of electricity between them. He constructed a pile of copper and zinc discs, with a moist cloth between each pair or couple, and by connecting wires from the top copper disc to the lowest zinc disc, he was able to show that an appreciable current of electricity was produced. Later he placed a piece of copper and a piece of zinc in a vessel containing acidulated water, whereupon he found that a steady current of electricity was obtained. This was the invention of electric batteries. The phenomena of magnetism were known to the ancients, but it was not until the 19th century that we found any real connection between electricity and magnetism. In 1819, a Danish philosopher, Hans Christian Ørsted, discovered that an electric current passing in a wire affected a magnet in its neighborhood. If the magnet were supported on a pivot, after the manner of a compass needle, it would turn round and take up a position at right angles to the wire carrying the electric current. The molecular theory of magnetism presumes that every molecule of iron is a tiny magnet, having a north and south pole. In a piece of unmagnetized iron, these tiny magnets are all lying so that they neutralize one another. When they are turned round so that their north poles are all lying in one direction, then the iron is said to be magnetized. The electron theory of magnetism does not do away with the older molecular theory just referred to. The electron theory goes a step farther, and tells us that these molecules are magnets because of a steady motion of electrons around the atoms of iron. It was discovered in 1825 that when an electric current was sent through an insulated wire wound around a piece of soft iron, the iron became a magnet. When the current was stopped, the magnetism disappeared. Such magnets are called electromagnets. If a piece of hard steel is treated in the same way, it becomes a permanent magnet. It was this intimate connection between electricity and magnetism, or in other words, the invention of these electromagnets, which brought us electric bells, telegraphs, telephones, dynamos, and electric motors. It should be noted that while iron is attracted by either pole of a magnet, there is such a thing as magnetic repulsion. This, however, takes place only between two magnets, and then only between like poles. Some German physicists made a number of electrical experiments with vacuum tubes. When Sir William Crookes, England, was experimenting with similar vacuum tubes, he suggested that matter was in a radiant state during the electric discharge within the tubes. In 1880, H. A. Lorentz of Amsterdam declared that light was due to the motion of small particles revolving around the atoms of matter. Professor Zeeman of Holland produced experimental proof of Lorentz's theory. He showed that the revolving particles were influenced by a powerful magnetic field, in the manner explained in the electron's story. This discovery was made in 1896, or 16 years after Lorentz's declaration. It was Dr. Johnston Stoney of Dublin University, Ireland, who christened these particles electrons. The X-rays were observed for the first time by Professor Roentgen of Germany in 1895. The screens used for viewing the luminous effects produced by the X-rays are coated with very fine crystals of barium platinocyanide. These screens were in use for another purpose previous to the discovery of X-rays. We know now that chemical affinity is merely electrical attraction between the atoms of matter. The spectroscope consists of a glass prism, or series of prisms, mounted between two metal tubes. One tube is provided at one end with a vertical slit, through which the light that is to be examined is passed. At the other end of the tube is a lens, so that the beam of light from the slit emerges through the lens as a pencil of parallel rays. The pencil of light then falls upon the glass prism, striking it at an angle. In passing through the prism, the light is bent round so that it enters the second tube, which is simply a small telescope. The prism separates the ether waves according to their wavelengths and produces the well-known colored spectrum, which is magnified by the telescope. The reason for the bending of the different waves is explained in the electron's story. End of the appendix. Recording by Laura Victoria. End of the Autobiography of an Electron by Charles R. Gibson.